Well, good afternoon and thank you for attending. I'm involved in something a little bit like Wayne, and nothing as sophisticated as some of the earlier technologies you discussed, but essentially I make extremely lightweight materials from waste. I take agricultural waste fiber and the like, and so let's look at what our impetus was. I looked at a product some years ago, stumbled over it as it were, something called autoclaved aerated concrete. And I looked at AAC and I thought it's an interesting product. It's got a lot of advantages, but it has a number of disadvantages. Clearly today everybody's interested in green credits and in new ways of building, perhaps methods of looking at getting the building to close up as quickly as possible. And it was interesting to see the straw board, the history of straw board, and in fact to some degree that's been a bit of our nemesis, because trying to get anybody interested in anything new that has to do with straw or fiber anymore is a bit of an uphill struggle, which explains why perhaps it ended up in China instead of North America after that brief history. So anyways, let's take a look at this. This is autoclaved aerated concrete, and essentially what you see here, it's a lightweight cellular material, but it's cooked in an autoclave. So here we see these large super panels here, which are, oops, that was the wrong way to go. I got the wrong button. Sorry, gentlemen. Let's do this again. I won't use the laser. I'm likely to mess it up. There you go. There's the laser. So these are super panels, and then these are the individual blocks. Again, very popular building material in the southern states, and we'll see why in a couple of minutes. The advantages of the product then is that it's cost effective. In fact, heating a building can cost you 6 times more money than it can be to heat it. Cooling a building can cost you 6 times the cost of heating it. Energy prices are increasing. We don't see them going down for a while. And people are looking for opportunities to decrease the cost of heating and cooling a building, cut labor inputs, and reduce the time to completion for occupancy. However, so here's some of the advantages of autoclaved aerated concrete as it is today in the marketplace. It improves the thermal insulation, it's non-combustible, it's fire resistant, it provides protection from termites and other boring insects. It has an established market presence. We don't see much of it up here, and I'll talk about that in just a minute, but in fact it's well known, and so there are engineering tables and criteria already established, and it is accepted in a number of building marketplaces, southern states in particular, and very, very well known in Europe. However, there are some disadvantages to autoclaved aerated concrete, and this was the impetus to look at ways and means of making it better. It has a very high capital cost. It's $26 to $60 million for a plant and facility. It's a fixed location, so clearly transportation cost of getting the finished product to the building site can be an issue. There are limitations in size and shape. Essentially, you're dealing with an autoclave, which is a large pressure vessel, and so you can only make a part that'll fit into the autoclave. It's a 12-hour production cycle. From the time you add the wet material to the dry, you tie up most of your equipment for 12 hours at a time. So if you've got $26 to $60 million in capital equipment and you've got a 12-hour production cycle, it can have a profound impact on your productivity and throughput. It uses only virgin materials and fresh water. We'll talk about that in a minute. And it has a limited fire resistance. So our objective then in looking at an alternate was to create a system that had the lowest capitalization possible. We looked at producing a portable production facility that could be in fact moved to the job site or close to the job site and produce the product on or close to the site. We're looking for continuous throughput. So in fact, you'll appreciate in an autoclave, you're dealing in a batch production environment. In our case, we're looking for continuous throughput, which would significantly improve the throughput of the equipment. We're looking for flexibility in the machine time. We want to cut that 12-hour cycle down as low as possible. And we're looking for flexibility of throughput. And one of the things that we've done most recently, which has been a big interest in the Middle East, is we've been making this material using salt water. And if you appreciate that 95% plus of the water on the planet is salt water, if it isn't an issue today, it won't be very long before fresh water becomes a major issue. So let's take a look at the outcome. We've been successful in achieving all, if not most, of these objectives. In fact, we've been successful in adding a significant green element, which is why I'm here today, because we're looking at using agricultural waste fiber and/or agricultural wood fiber as our input. And of course, we're looking for some significant advantages in terms of lead appeal. How's my time? So let's look at the results. Capitalization, okay? We've gone from a $26 to $60 million capitalization. We've had a unit designed at the U of A that will produce 10 cubic meters or 350 cubic feet per hour of this lightweight material for about $1.5 million. The unit is portable, so in fact it can be moved to the location of best utilization. It's a continuous throughput. So at 350 cubic feet per hour, we ran some numbers. We could produce 8 to 10 low-cost houses a day based on 800 square foot for a house, based on a 4-inch wall, and have all the perimeter walls for the house produced 4 to 8 houses a day, depending on the throughput. Significant advantage in terms of throughput. And we've also cut the production time from 12 hours to a continuous throughput, but also to the point where the molds can be reused every 4 hours. So you're casting a wet slurry into essentially a tray. The wet slurry is flowing at 350 cubic feet an hour. All you've got to do is keep the trays or the molds moving, and if you're on the job site, you can literally stack the trays as you might do in a precast concrete application, except we're dealing with a product that has a density of about 26 to 40 pounds per cubic foot instead of concrete, which is 160 pounds a cubic foot.